All right, so we know how to correctly identify forces, Newton's third law. We know how to correctly identify a good reference frame, point of view, for us to apply Newton's second law. That's Newton's first law. Now with all that, and the machinery we've developed in the last 9 modules or so, we can use that to apply Newton's second law, the dynamical law, that tells me for a given object that has mass m, if I can calculate the net acceleration, the net force acting on that object, that net force is equal to the mass of the object times the resulting acceleration of the object. We're going to work with particles for right now, or at least I'm going to treat everything as point particles versus extended objects, big solid objects that have many, many individual particles if you want to take the atomic view as the smallest particle that there is. These things have mass, which mass itself actually is subtler than you might think. I'm not going to go really into it. I think your textbooks will talk about this a little bit, but the m you see in F equals ma is what's called the inertial mass. It was kind of defined in the sense to be the resistance of an object to motion. You know, the idea that if I have a bowling ball and a tennis ball, and I kick both of them with the same force, clearly the tennis ball goes flying where the bowling ball does not. Now the reason is that there's this quantity called the inertial mass, which is acting as a measure of how resistant an object is to, if it's moving, to stop moving, or if it's not moving, to start moving, or to change its motion, which again requires accelerations. This measure of resistance, we're kind of familiar with, but then when you start diving into things, you can talk about things like inertial mass versus gravitational mass versus rest mass versus relativistic mass, and which mass is that Higgs boson field supposed to be telling us about, and which actually is applicable when we perceive the presence of mass, and you can get into the weeds real fast. Though I will say, since, and most of that does not apply to us in a classical sense. The one where it does apply, actually, which is kind of interesting, is the ma you get from Newton's second law, and then the m you get when you say have a force that is gravitational in nature, which by Newton's universal law of gravitation, he wrote it down as some constant g times the product of the two interacting masses divided by the square of the distance between them. The fact that this inertial mass and this, which you might define to be the resistance to motion in a gravitational sense, which is the interaction over long-range forces, it's not obvious that those should be the same thing. Why should the way a mass behaves gravitationally necessarily be the same that the way that mass behaves when I kick it? So this equivalence between the inertial mass and the gravitational mass, actually, by calling them equal, it's what's known as the, it's part of Einstein's equivalence principle. More concretely, it's the weak equivalence principle in this case, where we've declared that these two little m's are the same thing. Though again, it's not obvious that they should be, just, by looking at the equations themselves and thinking about what these equations represent. So I looked it up, and people have done measurements for decades to show that these two masses indeed do seem to be the same in magnitude. And as of 2022, there was a spacecraft that was launched by the French Space Agency in the late teens of the 2000s, which conducted experiments to measure the equivalence between this inertial mass and this gravitational mass. The way that's done on Earth is you can have kind of two masses that are kind of near one another so that they should gravitationally attract one another, and you can have one attached to kind of like a torsion or like something that's wound up, and so gravity will cause them to kind of attract, but then the torsion spring kind of wants the mass to not go all the way, but it kind of reaches some sort of equilibrium point. And the amount of twisting depends on the inertial mass, and the amount of gravitational pull depends on the gravitational mass, and you can confirm that it does seem that they appear to be the same. And people have gotten it down to like 10 to the minus 10 with those experiments. This experiment that was done up in space through a different mechanism at least confirmed the weak equivalence principle that those two masses were the same thing to more or less 1 part in 10 to the minus 14. Saying 10 to the minus 15 here, but this eta thing that they're measuring is something slightly different. It's the difference of the ratio of two masses. But when you disentangle it for a given object, it seems that its gravitational mass, whatever that is, and its inertial mass, whatever that is, at least seem to be the same to one another to at least 1 part in 10 to the minus 14. So pretty darn similar. If they are actually not the same thing, they are pretty darn similar. Similar enough that for this class, we are definitely going to say they are the same. And by the equivalence principle, it's usually assumed that they are the same. That's the kind of weak equivalence principle. The kind of strong equivalence principle generalizes it a little bit more. I think it allows things to be kind of self-gravitating in that sense as well, versus being acted on by some external tug or pull. So we're going to take the masses to be the same. That's all I'm going to really say about masses. So I want to do 3 absurdly simple examples, but I really want to go through them slowly and to kind of demonstrate how you can approach these sorts of problems, because any more complicated problem really is just applying the same sort of idea that I'm going to show here. First, let's start just conceptually. So suppose I drop a box. It hits the ground and eventually comes to rest. And I want to talk about the forces that I believe are acting on the box. Not knowing really anything about what their magnitude should be, at least in an absolute sense, but relatively, can I say what forces are acting on the box, and relatively what I expect the magnitudes to be. Forces acting on box. And this actually needs to then be broken up into 3 stages. There's the part where the box is kind of in the air and it's falling down. There's the part where the box has just made contact with the ground, so it still has some non-zero velocity, but there's kind of the point where it's being brought to rest. And then eventually the box is stationary on the ground. Now again, if I wanted to think conceptually about this, I could ask, if I want to study the box, what is touching the box in these cases? For the first case, nothing's touching the box. So there are no contact forces that should result on this box. So then once I've identified all the contact forces, in this case none, I can ask, is there any long-range forces? In which case, I expect there to be a gravitational force on the box. In all these cases, I expect there to be a gravitational force on the box. There's no reason why gravity suddenly turns off when it hits the ground. There's a gravitational force, the long-range force, on the box in all of these cases. In the first case, that's it. So if I know that the net force is proportional to the resulting acceleration of the object, I can't take one vector that's non-zero and somehow add it up to something to make it 0. So it does look like F net, in this case, which is just F gravity, is non-zero. So I expect the acceleration to be non-zero, namely I expect it to be pointing downward. I therefore expect the velocity to change. I'll just write that as delta V is non-zero. In this case, I expect it to speed up. And that's just by ideas of vector addition and vector calculus. If the box was initially moving upward, I would expect it to slow down, come to rest, and then speed up. In this middle case, it is touching the ground. So I expect there to be a force from the ground. So I could just start by drawing the arrow like this and say force from ground. Really, I should be drawing, well, remembering that these are vectors. Now in the case where it has made contact with the ground, I know, playing the movie forward, that it has the nanosecond before it touches the ground, it has some non-zero velocity. Then once it touches the ground, it starts to slow down. And in this case, it seems like it slows down very quickly. You know, I imagine probably a millisecond, maybe even smaller, that it needs to actually come to rest. That means during that small period of time, let's call it a millisecond, I went from having a potentially very large velocity downward to it being brought to zero. Now, if I want to change this velocity vector so that it goes to zero and essentially shrink its magnitude down to zero, well, I need a different colored pen. That means I need a very positive, large acceleration. Positive if I define up to be positive. I should have made that more clear at the beginning. That is in opposite direction because I know that changes only the magnitude of the velocity vector and it could shrink it down over some period of time to zero. So in that case, knowing if velocity starts pointing down and then goes to zero, it has changed in the sense that the velocity has kind of started to veer itself. It didn't start to go up, but it kind of veered up and then stopped. That suggests a very large acceleration pointing up was needed to get rid of that velocity vector in a short amount of time, if change of velocity over change in time is acceleration. You had a change in v, which essentially went from v final, which is 0, minus v initial, whatever it was, right before it touched the ground, divided by delta t, and then that is the acceleration. So it's an acceleration that, looking at the vector notation, points in the opposite direction as whatever the velocity was right before it touched the ground. That's why I drew it up and not down. And it might be, since it was done in a very small amount of time, small denominator, a very large velocity. Velocities result from forces. If there's an overall large velocity, that means there's likely a large, depending on the mass, but if I take a typical mass, it's called 1 kilogram, the large acceleration then means that there is a proportionally large force as a result. So it could be even a little bit more exact. And I expect probably that this contact force from the ground is much, much larger than the gravitational force, such that when I add these two vectors together, the net force is going to be non-zero and point upward, so that as a result, the acceleration is non-zero and points upward, and it is pretty large. Once it comes to rest, well, the velocity is 0 and it remains 0. That suggests no acceleration. So if there's no acceleration, then that means there can't be a net force, because I have established that I'm working in a frame where that is true. No net force means that whatever this vector is, it better be it better be in the exact opposite direction and equal in magnitude to the gravitational force. Again, not because they're Newton's third law of pairs. But in this case, it is the result of the dynamical law, the second law, that they are equal and opposite in this case. So in this case, F net is 0, which means the acceleration is ultimately 0, such that if v is 0, it stays 0. Again, just by asking what the forces are doing, how the accelerations are appearing, whether or not they're there or not, you can say something about the relative magnitudes of forces. And again, not to confuse, no force did I write down here was a Newton's third law pair to any other force I wrote down here. All right. So that we can do some things that are a little bit more quantitative, let me introduce Newton's universal law of gravitation. So gravitational forces a la Newton's. which says that if you have two masses, and I'll call them mass 1 and mass 2, they tend to attract one another. M1 is pulled towards M2, M2 is pulled towards M1. So if I want to write this in terms of what's going on with mass 1, it is going to feel a force that pulls it in the direction as shown by that arrow. Now what I should do is I should lay down a coordinate system first. So here's my coordinate system and my origin. The axes give me a sense of what I'm calling the positive direction in this case. In which case I can write a position vector for mass 1. I can write a position vector for mass 2. And then this here I might call the vector kind of 2, 1, which if you remember, seems like it points from 1 to 2, or to mass 2 from mass 1. Newton's law of universal gravitation says that the gravitational force on 1 from 2, which I usually will just use F sub g when the context is clear, is, since it's on 1 from 2, that means this force better point from 1 to 2. So it better point in the same direction as what I'm calling r sub 2, 1. And it has a magnitude given by g, m1, m2, all divided by the distance between them squared, so r2, 1 vector squared, and it points in the direction of r2, 1. So I'll write that as a unit vector, since the unit vector encodes the direction. The overall magnitude is this thing in parentheses. And you might say, wait, where's the minus sign? Well, you'll see in some books it is written in a way such that there is a minus sign. But that is because they are making a choice on how it's defined. If there was an overall minus sign here, you might see this, the way I've written it down, as, the force on 2 from 1. In that case, then the minus sign gets the direction correct. I prefer, if I can avoid ever having to deal with minus signs, to not have to deal with minus signs. So I write it this way, right? The vector, particularly the unit vector out on the right side, there's where the directionality is encoded. Give me the two position vectors, I'll take the difference. That tells me the direction of this particular gravitational force. The thing in parentheses tells me the magnitude. This is the general true statement for how two objects gravitationally attract one another. Very often in our examples and how we deal with gravity in our everyday lives, we are dealing with this gravitational force near the Earth's surface. Where the object is being gravitationally pulled by the Earth is being gravitationally pulled by the object. Typically, and we'll do this as either an example in a video or in class, the motion is only happening with the apple in this case. So the Earth is moving as I throw this apple up and down. The Earth is being moved gravitationally by the motion of this apple. But given that the Earth is so much more massive, or has this inertial resistance to wanting to move, we don't feel the Earth moving as I toss an apple up and down. The apple does all the moving. Kind of similar to how the sun, as the Earth goes around the sun, usually we approximate the sun as being perfectly stationary as the Earth moves around. It's technically not true, because again, by Newton's third law, gravitational force of on sun from Earth, there's also a force on Earth from sun, then there's also a on sun from Earth. The sun is also feeling a tug, though it has a lot more mass. So it's not perfectly stationary, but it more or less kind of just wobbles in place. This actually was important in the 90s, because this is how, for a long time, was one of the only ways we could find other planets outside of the solar system. We would look at distant stars and notice whether or not they were wobbling. If they were wobbling, we had to infer something was causing them to move, and we can infer that it must be planets, or what we call exoplanets now. But back down to Earth. Forgive the pun. Near the Earth's surface, what are we dealing with? If we're dealing with gravity from the Earth, usually we're dealing with, say, some object that has a little mass m. It is being pulled by the Earth that has mass m Earth. Remember that circle cross is the astronomical symbol for the Earth. And I won't go into this now, but the distance between the two objects, as you put into Newton's law of gravitation, for spherical objects, you go center to center. So the Earth, which has a radius equal to the radius of the Earth, about 4,000 miles, the distance between the two objects is this distance here. I'll call it little r. Now that little r, if you're near the surface of the Earth, is often approximated to be essentially the radius of the Earth. While this apple and this apple are technically at different distances from the center of the Earth, this 12 inches that I've moved it, 12 inches compared to the 4,000 miles that's the radius of the Earth, who cares about 12 inches? That's more or less the same thing. 4,000 miles plus 12 inches is more or less 4,000 miles. So this approximation of when we say you're near the surface of the Earth is that we're taking that the distances you're dealing with relative to the ground are small compared to the radius of the Earth. If you want to talk about the moon, you cannot make that approximation. If you want to talk about a spaceship that's trying to leave Earth and go to the moon, at first you can make that approximation, but the higher and higher it gets, that becomes a less and less valid approximation. So in this case, the force of gravity on the object from the Earth then is g, the mass of the object, the mass of the Earth, divided by the radius of the Earth squared, approximately. This can be rearranged, so that's the mass of the object in question, and then there's a bunch of constants that never change. As long as you're near the surface of the Earth, this thing in brackets is more or less always the same, because you're not dealing with the small changes in distance. You can look up these numbers, plug them in. It ends up evaluating to 9.81 meters per second squared. So near the center of the Earth, we can write that as the gravitational acceleration from the Earth. But what is it arising from? The real force of the gravitational interaction between the object and the Earth. All right. With that in mind, let's do, how much room do I have? Let's move. Let's go to the simple kinematic problem. Let me do it generally, because I feel like we have the sophistication to do this now. Let's see, at t equals 0, a ball is located at position r0, which I'm going to call, it's a 2D vector that is coordinates x0 and y0, above the Earth's surface, which the Earth's surface is kind of being defined as y equals 0 in this case. And moves at speed v0, which is some initial velocity in the x direction, some initial velocity in the y direction. And the question is, I now want to determine the trajectory, or determine the motion of the ball, which has mass little m. Okay, so pretty simple physics problem. But again, hopefully it won't be too painful to go through this in detail, focusing, I would say, focusing more on how I'm approaching figuring out this problem compared to what the exact solution is. So first things first, I will identify the system that I'm working with. So the system in this case is going to be the ball. And I want to determine the motion of the ball. So I'm going to call that my system. To do this, I want to put myself in an inertial reference frame and then establish a coordinate system so I can describe this quantitatively. I'm going to use the surface of the Earth and approximate that as my inertial reference frame. Again, we know that's not exactly true, but to a good first approximation it is. So we're going to take it as our inertial reference frame. I've written down a coordinate system where I am establishing directions and I'm establishing the location of my origin, so that I can, in this case, know that this is the initial position of the ball, which might have some velocity, which maybe its initial velocity is like this, I don't know. It can be whatever, right? I kept this pretty generic. And then the question is, what is the ultimate trajectory of the particle? Right? We know it does kind of something like that as time moves forward. My choice of coordinate system, the origin, kind of up to you, right? I could have put the ball at the origin to begin with. I chose the origin such that y equals 0 was the ground. And I could have had x start at 0. That would have actually just said that x naught equals 0 in this case. But let me put my coordinate system down there, and then that is my initial position. And then given those coordinates, those axes, that directionality, I can write down the initial position, r naught, and the initial velocity, y naught. I kind of did those out of order. Right? Really, you establish your coordinate system before you can write down a vector, because you need to know what the axes are. Now, I think with all that, we can then go on to identify real forces. What are the real forces acting on the ball? I would say, just first ask myself, is anything touching the ball? No, nothing is touching the ball. If we're not including air resistance or anything like that, which we will not. So then I can ask, are there any long-range forces? And indeed, there is a long-range force, which I expect to be the gravitational force on ball from Earth. And given what I wrote on the previous page, I can now say something about what that force looks like as a vector, to give it some directionality and give it some magnitude. Given the drawing on the previous page, which has said this explicitly, let me just go back to it real quick. Given this drawing on the page, this is pointing, in the case of when you're near the surface of the Earth, Fg on the object points towards the center of the Earth. So in this case, where I've kind of zoomed in on a small patch of the surface of the Earth, so that I can draw the surface as kind of a flat surface beneath without any sort of curvature, that means that gravity is going to point downward in this case. So that's a good choice of coordinate system that I made, because then that means one of the coordinates of this vector is 0. Always choose coordinate systems to make these things as simple as possible. And then in the second term, or component rather, I can write it as minus mg. Now I'm going to pause again to highlight this minus sign. Why is it a minus sign? This is established by the coordinate system. The coordinate system, which, notice I said positive in the y direction, is up. So since I know gravity is going to want to point towards the center of the Earth or towards the ground, that is why I need a minus sign there. I could have made the axes point in a different way. Then maybe it would be plus mg, or maybe there'd be two terms, or two components rather. But again, I chose the axes to be what they are, which made one of these components 0. The other one is a negative. That negative, again, I want to always make it clear when you have to have negative signs. Is this a negative because of the coordinate system, or is this a negative because of something else, which we'll see in the next problem. Okay, that being said, looks like then I can say the resulting acceleration is given by F equals ma, where the mass of the ball times the acceleration of the ball is equal to the net force on the ball, which in this case is just the gravitational force acting on the ball. This is a vector expression. Mass is a constant. The accelerations are two components that I'm trying to figure out. And that equals, in this case, 0, minus mg. I've introduced the actual components of the vectors only at the very end. Work generally with vectors first before you actually break it into components. And again, that's kind of obvious in this case, and we'll see in the next example where that can be helpful. So this implies, it looks like, that the acceleration in the x direction is 0, or 0 divided by m, and the acceleration in the y direction is negative mg divided by m, or just negative g, a constant equal to 9.8 meters per second squared. Great, but we're not done. We want to determine the motion of the ball. That means I want position as a function of time. Here's where the differential equations come in. Differential equations, I know by definition that the acceleration is the derivative of velocity. If I treat the derivative as a ratio, and again, the mathematicians will scoff, but we can do this and get away with it. I can treat this as a small change in the velocity vector. How does velocity change? It's more or less what the left-hand side is saying, is equal to acceleration times a little dt. Velocity is changed by an accelerations applied over time. This then leads me to evaluating the actual change in the velocity, which I can do by integrating. Integrating over what? The left-hand side is an integral over velocity vectors. So I could write this as it's going from some initial velocity vector v, that kind of brings in what I know about where the particle started, and it ends at some final velocity, which I'll just write as some generic v. The right integral is integrating over time instead, so my limits can't be v. The limits in this case have to be the times that are associated with the v's. So I know that this is when the velocity is equal to v naught at t equals 0. So that is why these two are connected. And then I'm going out to some generic t, in which case the velocity is some generic v. The integral of the left is ends up just being v minus v naught. And the integral, since the acceleration vector is a constant vector, ends up just being the acceleration vector t minus 0 in this case. Now I'm doing this as vectors. You can do it by component, and sometimes you have to do it by component, where I could have explicitly said from here that this says that the change in velocity in the x direction over time is equal to a sub x, which is 0, so that the change in the velocity in the x direction equals 0 times dt, integral the initial x velocity to some final x velocity, going from 0 to t. And then when I'm done with that, also solve the same thing for the y direction, which would give me a second integral to solve, which would give me a different answer for what the final velocity is in the y direction. Since the vector is a constant, they come to the same answer. So it looks like this is saying the final velocity, and I'll even be explicit, say at some time t, is equal to the vector v naught plus the vector a times t. T is a scalar. Usually we put scalars up front, but in front of the vector, but I think this is kind of how we're all used to seeing this. So if I wanted to write this as a vector, it looks like that was the initial x velocity, initial y velocity, plus, then I multiply a t through, t times 0 is 0, and then negative gt. So the velocity vector at some time later t looks like it's v naught x, comma, v naught y minus gt. That should hopefully look familiar. All right, so, and then that gives me velocity as a function of time. Tell me a time, I'll tell you the velocity at that point. Are we done? No, because I still don't know positions. Well, as you can imagine, the same thing can happen. I know that velocity is the change in position over time, so that the change in the position vector is going to be the velocity vector times dt. I can integrate both. Again, going from some initial time, which 0 to t. Then that must be the initial position vector, because the limits are not the same, but they're associated with one another, to some generic time r. I can again be explicit at some later time t. The left integral becomes that. And the right integral, in this case I have to be a little bit careful because the velocity vector is not a constant. The t exists inside the velocity vector. So in this case, it might actually be easier to do this component by component, right? So this would be the integral of the first term, the initial velocity in the x direction, times dt from 0 to t. And then the second term, or component rather, is the same integral, but is the second component over dt. This is not too bad. The first component, it's the integral of a constant. The second component, in the first term, is a constant, and then good old polynomial rules. The antiderivative, of course, is negative 1/2 gt squared, but then you have to evaluate that at the top limit minus the evaluate at the bottom limit. But the bottom limit, it's 0 because t squared goes to 0. And that equals r as a function of t minus the initial position. So then it looks like r as a function of t is r naught plus that mess, which then when you bring that in, it looks like it's going to be the initial x position plus v naught x times t. And the second component is the initial y position plus y naught, or v in the y direction naught times t, minus 1/2 gt squared, which is the answer. And that just looks like what is usually called the kinematics equations, which get overused. Do not blindly use the kinematic equations, please, unless you know when they're applicable. This was done, really, the kinematic equations, these final two equations here for x and y, were arrived at and only were able to be derived because the forces that were acting on the ball resulted in constant accelerations in the x and the y direction. And the x direction happened to be 0, the y direction happened to be a constant, which we called negative g in this particular coordinate system. That negative in front of the 1/2 there is a result in this case because of the coordinate system choice we made. So again, don't blindly start plugging these things, using these things unless you know when they apply. And I've done this very generically so that the x naught, the y naughts, the initial velocities, they themselves could be positive or negative. That would, again, if they were positive or negative, that would depend on what they are doing relative to the coordinate system I've laid down. Which, again, is why it's always nice to kind of work without minus signs. And be very careful when you do have minus signs of whether it's a coordinate system result or something else. All right, how much space do I have? I think I'll go to the next page. The last example I want to do brings in one of these contact forces. I wanted to say something about active versus passive forces. Gravity is kind of an example of an active force. The equation we have is kind of a simple, straightforward, and it's always the case that the gravitational force on the object is negative mg, if we stick with the coordinate system from the previous problem. If I push on a box, that's an active force, right? Which is kind of easy to imagine. There's an agent kind of actively pushing on the box, and I can say that I'm pushing on the box with some amount of force, 10 newtons or whatever I decide on. They have values that are established either by the constraints or the agents acting in that case, or established by, say, models. Like, for example, a spring force, for example, and the amount of force depends on, the amount that the spring is stretched or squished. That is in contrast to passive forces, or often what they arise in the form of constraint forces, where the actual magnitude of the force can change depending on the system. Usually it changes in order to make sure a constraint is ensured. For example, I have this apple and I'm touching it. Actually, let me use something that's not a human. I have my journal, and I put the apple on the journal. If it's just sitting here stationary and gravity has not gone anywhere, gravity is pulling the apple down, and so as a result, the fact that it's also touching the journal is pushing back up on the apple with a force that ensures that the acceleration of the apple is zero. And so, since it has zero velocity, that stays the case, and its velocity remains zero. The book, there's no, all journals exert the same force, right? It's that the journal decided that that's the force it needs to do to constrain the apple to not move through the book. If they were not in balance, if mg was greater than the force of the book pushing back, then that says by Newton's second law there should be an acceleration downward and the apple would start moving through the book. Similarly, the apple is not flying off the book, in the case if the inequality were the other way. But then I could push down on the apple with my finger. You can notice the book is kind of bending a little bit as a result of my push. Now, am I touching the journal? No, I'm doing nothing to the journal. I'm not exerting any force on the journal, I'm only exerting on the apple. But the apple is exerting a force on the journal, and I think we all would agree that the book or the journal then has to push back on the apple with more force as a result. The magnitude of the contact force between them has to change to compensate for the constraint that we still don't want the apple to move through the surface of the journal. Right, so this is a kind of example of a passive force where it will adjust its magnitude such that usually a geometric constraint is maintained. In this case, the apple does not move through the book. Static friction is another example. It can adjust its magnitude such that it ensures that there's no relative motion between the two surfaces. In that case, it can only do so much, and then eventually it becomes kinetic friction. So the normal force, as is often called, is an example of one of these passive forces. But again, I like to think of it as it's a contact force between the two objects, and it is adjusting its value such that it is what is, and it maintains some sort of geometric relationship. Usually in that case, it means that the objects are not moving through one another. So let's just look at that real quick, right? Suppose I have a box of mass m that is sitting on a surface. And rather than calling it a surface, I'm going to call it a scale. And nothing is moving. So it's stationary, which means the velocity of the box is 0. And again, what I'm studying here is the box, so I should this is my system that I'm studying. So the velocity is 0, and always is 0, so even velocity as a function of time is 0. It's terrible as a function of time. Which means the acceleration is 0, which means the net force on the box better be 0. Assuming I've put myself in a good frame. So in that case, I can identify that it's touching the scale and there's a gravitational force. Not knowing anything about what the normal force needs to do, or the contact force there, I know gravity points down because I'm going to use, again, a coordinate system where up is towards the ground, up and down is kind of vertical away from the surface, and then x is horizontal to the surface. So in that case, I know the gravitational force points directly downward. Just by alone knowing that the net force has to be 0, I know that the contact force from the scale better be pointing up exactly up, no horizontal component in this case, and be equal in magnitude and opposite in direction to the gravitational force. Again, not because it's a Newton third law pair. So then I know the gravitational force plus the scale force better equal 0 in this case. That's very general, written down as vectors. Now, since I don't think there's anything else I need to do, I can bring in my coordinate system. And even if I didn't think, actually let me even stick generally. Maybe I didn't make that drawing in advance, and I know that there's a contact force, but I don't know what it should be. So I know the scale should push up in maybe in the x direction, and then maybe in the y direction. And I'll write them not with negative signs in front, but I'll write them both as just variables, which they themselves might be positive or negative. Let me let the math tell me. And that equals 0. Then you can solve, and it says, okay, yes, the x component better be 0 if these inequalities are being satisfied, and the y component better be positive m plus g, or that it points upward. Again, not too surprising, but the scale has adjusted itself to have this value to ensure, in this case, that the box doesn't keep going through the scale, establishing its stationary presence on the scale. If you were to think of this as then what are the forces on the scale, and suppose the scale's mass is very, very small, so we don't have to worry too much about gravity. In that case, that contact force of on mass from scale, then it's the negative of that. The scale then feels a force of F on scale from box. Where this up here, if I were sticking with the notation I should be writing in, on box from scale. And then it's also perhaps touching the ground that I have to wheel about. So then also it might be plus F on scale from ground as well. And if the scale is not moving, then I know that this also better equal 0. These statics problems, right, where v is 0, really we should be careful and say it's 0 as a function of time, which is really saying that there's no net acceleration. Here I've written them both as plus signs, even though I expect, again, the vectors to be pointing in different directions. And then I also know, by Newton's third law, that this is the same thing as negative f of on box from scale plus f on scale from ground. Where the negative sign I've introduced here is the Newton third law negative sign. Not because of a coordinate system. That negative is because of a Newton third law relationship. Then I can bring in, that this negative sign, and then I figured out on box from scale was 0, plus mg from the above problem, then plus kind of the ground forces, right? So the ground kind of on the scale, and then in the x direction, and then the ground in the y direction. Better equal 0. Which then again says that the ground in the x direction has no horizontal component, but then the ground in the y direction, that shouldn't be a vector, looks like it has to be also plus mg, because this becomes negative mg plus fgy equals 0. So this also is plus mg. The ground pushes up on the scale with plus mg to maintain this kind of geometric constraint. So I like scale because, again, there is a force on the scale that we just figured out, right? There's a force from the box pushing down on the scale. That first vector that we've written here, right, this, let me use a different color, right, this thing here, on box from scale. And I'm including the minus sign in that. Now, usually with a bathroom scale, that force that's pushing down on the scale, then the spring inside the scale squishes a little bit to create that restoring force that pushes back up. And the spring compresses as much as it needs to balance things out. All right. So I like this I like the idea of thinking of things as a bunch of springs, right? And that in this case, the scale has adjusted the amount of force it's pushing back up on the box such that to keep forces in balance. In that case, there's an agent. It kind of gives you an agent to imagine rather than thinking about passive forces. The agent being the spring inside the scale that's adjusting itself to then push back up with how much it needs to. So I like to think of normal forces as, say, the bathroom scale force, right? What the bathroom scale would read, because then inside the scale itself, it measures how much the spring is compressed and translates that to a number that it reads on the screen. I like that idea because then that gives you a sense, really, again, of what the normal force is, if you want to stick with that term. Right? I take this apple, and I don't know if it's on camera. Right? I can push it up against. I can push it up against my bookcase, and it's not moving because the bookcase is pushing back against. I'm pushing the apple. The bookcase is pushing back. That is the quote normal force, if you want to talk about it that way. Again, really, it's just the contact force between the bookshelf and the apple. But if I were to replace it with a bathroom scale and push the apple, right, I could push the apple against the bathroom scale and it would read a number, and it could change based on how hard I'm pushing against the wall. The bathroom scale, in that sense, is essentially measuring the normal force of that contact surface in question that is adjusting itself passively to balance things out. So I like the normal force, thinking of it as the bathroom scale reading, or force if you want to call it something like that. But that's an example of a passive force. And then, get rid of the scale and just have it be the ground. Well, the ground actually, if it's a solid, can be thought of as a bunch of very tightly wound springs. I punch a table, it will deform the table a little bit, and it will actually create a ripple that goes out from my hand. It's damped, so the ripples go away very fast, and they're very, very slight because you can think of surfaces as essentially being springs with exceptionally high spring constants, if you remember Hooke's law, right? So that they do have a resisting force, but usually you don't have to deform them that much for that force to balance things out, which is why I don't see the table bending as I push down the table. But I can push down on the book enough, right, so that it does start to deform, right? It's kind of acting like a spring that's trying to push things back up. So maybe I kind of did a Newton third law example above. Let's do it again, just to see how Newton's third law can be combined with using Newton's second law in a way that I make sure I get everything correct. Let's again, let there be a scale. Then there's two masses. One mass is on the scale, and then the other mass is on top of the other mass. Everything is stationary. And if this were a bathroom scale, which, again, you can think of it as it returns a number, that number being the force, the magnitude of the force of that normal component, I could ask, what does the scale read? Now, intuitively, you might think it should read not m times g, but it should, like it did in the previous problem, but it should read 2m times g. Your intuition is correct in that case, but we should be able to write down Newton's second laws in a way where I can calculate the force on the scale and get 2mg as a result, pointing upward, presumably in this case. Now, it would be incorrect to say that both masses are acting on the scale. Only one mass is acting on the scale. The bottom mass is touching the scale, so there is a contact force between the scale and that mass. The top mass is not doing anything to the scale at all. Yet, we are claiming that the scale reads 2mg. So we need to be able to write that down mathematically and actually figure it out. And we do this in stages. First, let my system be the top mass. It's stationary, so I expect the net force to be 0 in this case. So again, it's a static case where the velocity is 0 as a function of time. I don't want to get it stuck in my brain that 0 velocity equals 0 force. It's 0 is that there's no change in velocities ever, which is accelerations. So I know the net force better be 0 on this top mass. Then I could ask, what are the forces acting on the system? Well, there's the long-range force, so I expect gravity to be doing its thing. Then it's also touching the bottom. Actually, I should be explicit and use my longhand stuff. So there's a gravitational force on, and I'll call it top from bottom, where top and bottom will refer to the boxes. And then there's a contact force that's presumably going to be pointing up, a force on top from bottom, because the two boxes are touching one another. And that's it. It's not touching the scale. The scale cannot do anything to this top mass, nor can the top mass do anything to the scale. I'm going to simplify the math a little bit in that I know everything is going to end up being one-dimensional, so I'm not going to worry about writing down things as vectors. But I still, though, in my coordinate system need to define the positive direction, so I will call up the positive direction from my origin, which I will take to be the ground, if that's needed. In this case, for the top box, I know that F net, which is F gravity on top box from Earth. Actually, stop. What the hell am I saying here? Gravitational force on top from Earth. This is what you get when you record multiple of these in one sitting. There's a gravitational, but I only allow myself one take because I don't have enough time to edit these and do multiple takes. Sorry. So there is a gravitational force on top box from Earth. And then there is a contact force on top from bottom. And I know these better add up to 0. And again, knowing that I expect there to not be a horizontal component, I can just write these then on scalars. I don't know what this, I know that this is going to be negative mg, and I don't know what this is going to be, so I'll write it as a generic f t/b. That's going to equal 0. So then that suggests that the force on the top box from the bottom box is positive mg in the vertical direction. And that makes sense as I've drawn it, right? They better cancel each other out. Okay, let me redraw. Now let's do the bottom box. Oops, red is supposed to be my system. I know there's going to be a gravitational force, F gravity, on bottom box from Earth, gravitational. It is touching the scale. Anticipate maybe that's going to point upward as a result. So I have F on the bottom box from the scale. Then the top box is also touching the bottom box. So I might expect that there's another force. And maybe I don't even know what direction it's going to point. You could just write this generically. I know there's going to be a force. The fact that the top and the bottom box are touching each other means I need to be able to write down a force on bottom from what? From top, in this case. So there are two things touching the middle box, the bottom box. That results in two forces I've written down, and then plus gravity. And these better add up to 0. So then it looks like for the bottom box, I have F gravity on bottom box from Earth plus the contact force of on the bottom box from the top box touching. And then I have F on the bottom box from the scale, because they are touching. And that better add up to 0. Now I've not introduced which direction is the negative from the coordinate system yet, right? It's that Newton's second law says the sum of forces, which means add, equals 0. Before I bring in the coordinate system, which might have negative signs like negative mg, I'm going to realize that there's a Newton third law pair I can connect to the previous part. This is still gravity on the bottom box from the Earth. This is the bottom box from the scale, but this is negative the force of the top box from the bottom. Again, why I like writing force subscripts this way, because I can just flip them and I know that's the Newton third law pair. Which this thing, the force on the top box from the bottom box, we already figured out what that is. It's plus mg. But here, this negative sign, again, this negative sign, Newton's third law introduced this negative sign, not because of the coordinate system. Now, having identified all third law pairs that are going to be relevant, let me bring in the coordinate system. Gravity of the bottom box from the Earth, negative mg. The force of the top box on top from bottom, we said was plus mg, but then there's this overall negative sign that came from the Newton third law. Again, let me just make it very clear. That negative sign is from the Newton third law, not because of the coordinate system. And then plus whatever the force of bottom box from the scale equals 0. And then look at that. The force on the bottom box from the scale is 2 mg, positive 2 mg in this case. The scale has to push up on the bottom box with 2 mg worth of force. Even though, again, it is not touching the top box, but the scale has to adjust itself to be pushing up with 2 mg. That holds both the bottom box and, through contact forces, the top box where they are. The bathroom reading scale, then, what is the scale which is only touching the bottom box? Then is negative 2 mg, which gets then translated into a number, which is read on the bathroom scale reading. Or if I included then, if I did a force analysis of the ground, there'd be force on scale from bottom box, plus F from the ground on scale from ground. And the ground has to be pushing up on the scale with 2 mg if we don't give them scale any mass. All right, so again, simple problems, but kind of hopefully that gives you a sense of how you can establish and write these things down in a very systematic way. No guessing involved. And then no matter how complicated you make these things, I could throw in pulleys, and some of the problems will have pulleys and lots of other, or actually not yet, no pulleys yet, we need to do tension. But I can make it this as complicated as I want, but you're just looking for what's touching, and then is there gravity.